Okay, we're continuing our derivation of the Laplace transform of cosine of omega t, which, just following the definition, it's an improper integral, which I've written in limit form right here. Now, we determined that in evaluating this integral, we needed to use integration by parts, and I showed you a nifty shortcut of tabular integration by parts that essentially says we're going to get this diagonal product minus this diagonal product plus the integral of this row. And I created this table by just starting with u and repeatedly taking the derivative, because this was my first u prime, but it becomes my second u. So the second time I did integration by parts, this was u and this was u prime. This column, I start with v prime, and I just repeatedly integrate. This was my first v prime, so this was my first v. The second time I did integration by parts, this was my new v prime, this was my v. Okay. So we will take the limit eventually. What I'm going to do right now, though, is just write out what this integral is using this shortcut of tabular integration by parts. So the integral from 0 to b of cosine omega t e to the negative st dt is this diagonal product, which is negative 1 over s cosine omega t e to the negative st evaluated between 0 and b, minus this diagonal product. Now, minus and then a negative, that's just going to become plus omega over s squared sine omega t e to the negative st evaluated between 0 and b. All I did was bump the constants to the front. Plus the integral of this row, which is going to be a negative omega squared over s squared, again just bumping those constants to the front, cosine omega t e to the negative st dt. Okay. All right, to clear up some space, I'm now going to erase the table because we've used it. We've got our lovely results. Now, if you notice, this is just a constant. I could bump that outside. So if I do that, oh, and I'm sorry, I left off my limits of integration. This is still a definite integral from 0 to b. But what I'm doing is I'm just moving that constant outside. So it becomes minus omega squared over s squared times that integral. Now notice, this integral is exactly the same as this integral. And that's what I want to solve for, so that I can then take the limit of it, because that's going to be my Laplace transform. So what I'm going to do is take this and add it over to this side. So right here I've got one copy of the integral. Here I've got minus omega squared over s squared copies of the integral. When I move it over, I will have 1 plus omega squared over s squared copies of the integral from 0 to b of cosine of omega t e to the negative st dt. And what that is equal to then is this. So let's go ahead and work that out. That's going to be this evaluated at b, so negative 1 over s cosine omega b e to the negative sb minus what I get when I plug in 0. Now, when I plug in 0 for t, cosine is going to become 1. E to the 0 is going to become 1. So I'm just going to get a negative 1 over s. And of course, minus a negative 1 over s is just a plus 1 over s. Plus, now I'm going to get this evaluated at b minus evaluated at 0. So omega over s squared times sine of omega b e to the negative sb minus what I get when I plug in 0 for t. Now if I plug in 0 for t, sine of 0 is just 0, and so that piece drops out. Okay, so now I can solve for this integral. The integral from 0 to b of cosine omega t times e to the negative st dt is 1 over 1 plus omega squared over s squared, I'll probably want to simplify that eventually, and I will, times negative 1 over s cosine omega b times e to the negative sb plus 1 over s plus omega over s squared sine omega b times e to the negative sb. Excellent. Okay, I'm liking this. So that's what I get for my integral. Now, I want to take the limit of this thing as b goes to infinity. Okay, so I'm going to, just in the interest of space, so that was my integral. I'm done with the integration. Now I'm going to apply the limit. If I want to take the limit as b goes to infinity of this side, it's going to be the same as the limit as b goes to infinity of this side. There are no b's here. There are b's here and here. So I need to evaluate these things. Now remember, we stated in the last video that s was going to be bigger than 0. Now if s is bigger than 0, that means this is going to be e to a negative power, and that power is going to negative infinity, because b is going to positive infinity. So the exponential is going to go to 0. Now I'm multiplying that by cosine of omega b. Well, that's bounded. So this part does depend on b, but I know that it's bounded. I have to be careful, because if I'm multiplying two things together and one thing goes to 0, that doesn't actually mean that the entire product goes to 0, because I could have an indeterminate form. I could have, quote unquote, 0 times plus or minus infinity. In that case, I would need to use L'Hopital's rule to take the limit. But I don't have that, because that piece isn't going off to plus or minus infinity. That is bounded between negative 1 and 1. So that means the 0 is going to kill it off. So this entire term is going to 0. 1 over s doesn't have any b's in it, so it's constant with respect to b. This piece, same thing here. The exponential part is going to be going to 0 because s is a positive number. The sign is bounded. It's not going to plus or minus infinity, so this is not an indeterminate form. 0 does kill off anything finite, so that entire piece goes to 0. So, if I take my limit here, looks like I'm just getting this times this. Let me write that out. That's the limit that we were trying to evaluate. We've now got that that's 1 over 1 plus omega squared over s squared times 1 over s. Okay, let's try and simplify that, because that's a messy, complex fraction, but I think we ought to be able to simplify that and get something a little bit nicer. Okay, so basically with this being a complex fraction, what I would do is take that, let's just multiply that by 1 in the form of s squared over s squared, and then we're still multiplying by 1 over s. Now what that's going to give me is s squared on top over, when I distribute the s squared to both pieces here, I'm going to get s squared plus omega squared, because it'll cancel here, and then we've still got this other factor of s in the denominator. So I can cancel one of the s's. On top, I will get s over s squared plus omega squared. That is the Laplace transform with the restriction. Let's write this. S, remember, had to be bigger than 0. That is the Laplace transform of cosine of omega t. That's how we get it using the tabular integration by parts. Now, I was explaining the shortcut, so it wasn't particularly short. It is shorter if you just use the shortcut and don't write everything out to see why the shortcut works. Nevertheless, this isn't my favorite method for deriving the Laplace transforms, but some of you might like it, and I think it's worthwhile taking a look at how we would go about doing that. Great opportunity to review. integration by parts and that lovely shortcut that we have for making repeated integration by parts go a little bit faster.